quantum mechanics, we can also consider another operator associated with angular momentum. This is the operator L squared. This should be thought of as the vector dot product, as it were, of the angular momentum operator L with itself. And we can define it as Lx squared plus Ly squared plus Lz squared, where this, of course, Lx squared just means Lx operating after Lx, and similarly for Ly squared and Lz squared. Now, it's straightforward, although it takes a bit of algebra, to show that we can write this L squared operator as minus h bar squared times another operator, which we could call del squared of theta and phi, where that operator is given by this rather frightening looking expression here, but it's actually fairly straightforward. And this expression, which, as I said, we could derive merely by working through the algebra to get up to here, is actually the theta and phi part of the Laplacian operator if we choose to express it in spherical polar coordinates. That's why we call this the notation here, del squared theta phi. Now, L squared commutes with each of these operators, Lx, Ly, and Lz. And it's easy to see, for example, from this form that we have here, that we are going to be able to commute this operator with the Lz operator, because the d by d phi in here, well, it does nothing at all to this part, and d by d phi, of course, commutes with d2 by d phi squared. So this operator will commute with the entire del squared theta phi operator. So then we can see, at least therefore, that L squared and Lz commute with one another. And as I said, this operation d by d phi has no effect on functions or operators that depend on theta alone. Of course, the choice of the z direction we had here in defining L squared is entirely arbitrary. We could equally well have chosen the polar axis to be along, say, the x direction or the y direction. Then it would similarly be obvious that L squared commutes with Lx or with Ly. How can it be that L squared can commute with each of Lx, Ly, or Lz, but these operators, Lx, Ly, and Lz, do not commute with each other? The answer is that we can choose the eigenfunctions of L squared to be the same as any one of the sets of eigenfunctions of Lx, or of Ly, or of Lz. So what are the eigenfunctions of L squared? We want eigenfunctions of L squared, or equivalently of this operator del squared theta phi, and so the equation that we hope to solve is something we could write in the form del squared of some function of theta and phi, we still have to figure out, is equal to some number times this same function. Of course, in writing this down, I'm anticipating the answer, but at the moment, this L into L plus 1 is, with the minus sign in front of it, just an arbitrary number. We've still got to determine it, and these functions also are just arbitrary functions that we've still got to determine. But this particular notation I've used here anticipates the final answer, which will be things called spherical harmonics. But at the moment, this is still just an arbitrary function to be determined. Now, to proceed with this, we have to separate some variables, and we use the same standard technique that is always used in separating variables. We presume that the final solutions to this equation, the eigenfunctions, can be written in some factorizable form. So we've said this function of theta and phi, let's see if we can write it as some function of theta, and I've just used a capital theta here to name the function, times some function of phi, and I've just used a capital phi here. Now, as always in these kinds of separations, this is just a guess. The justification in the end is that we will find that this works, and it gives us general solutions of the equation. But at the moment, it's just a guess that we can get this to work. However, we can get this to work. And note that this function, capital theta of theta, only depends on theta, of course, and the function capital phi of phi only depends on phi. So we're going to substitute this form into this equation, And that will give us the following equation after a little bit of algebra here. And again, it looks a bit complicated, but it's actually all right. So we've taken this del squared theta phi operator that we wrote down before, and operating on this product here gives us this set of terms. So we've got some derivatives with respect to theta and a sine theta in here operating on this function, capital theta of theta. And we've got some derivatives with respect to phi operating on this function, capital phi of phi. And then we're left with other parts out here outside these derivatives. Well, we can take that whole equation and multiply it by sine squared theta over the product of capital theta of theta times capital phi of phi, and rearrange that, and then we get the following equation. So on the left here, we've got something that only depends on phi and is only a function of phi, and on the right we have something that only depends on theta and is only a function of theta. So the idea is, because this only depends on phi and all of this only depends on theta, then they must both be equal to a constant, something we call the separation constant. So anticipating the answer here, we'll choose a way of writing down that separation constant as minus m squared, but at the moment it's really just an arbitrary number. And this m is still to be determined. So once we've done that, we have two different equations. We have our phi equation from the left-hand side of all of this, being equal to minus m squared, our separation constant. So our equation then for phi, since it's only in one variable now, it's an ordinary differential equation, d2 capital phi of phi by d phi squared is equal to minus m squared times the same function. The solutions to this are quite straightforward. You can easily check that any of these will work. Sine m phi would work, cos m phi would work, or e to the I m phi would work. For the solutions of this equation, we're going to choose the exponential form, because then this same function will also be a solution of the LZ eigenequation. And that eigenequation was in the following form. So e to the I m phi is a solution of this equation, and it's also a solution of this equation. And we're going to make that choice here. We do have a choice as to what we have. Now, we expect that this function, capital phi, and its derivative are continuous. And that means, because this is a function of angle, that therefore it goes round in a circle and comes back on itself, this function must repeat every 2 pi of angle phi. So that means that m must be an integer. In fact, we already knew that from trying to solve this equation here. But this equation also has that same requirement. For the theta equation, we take the right-hand side of the separation equation, and we set that equal to the separation constant. And multiplying now by capital theta of theta divided by sine squared theta, and doing a little bit of rearrangement, gives us this differential equation here. So some moderately complicated derivatives with respect to theta here of our function capital theta of theta, and this set of terms over here. And these all have to equal 0. Now, this equation is what's known as the associated Legendre equation. And the solutions to this equation are known. They are called the associated Legendre functions. And we can write those in a standard notation in the following form. P with a subscript L and a superscript M of the cosine of theta. Now, these solutions to this equation require that L, this number here that we introduced, has to be 0 or a positive integer. And it also requires that m has to lie between minus L and plus L, and it has to be an integer. These associated Legendre functions can be conveniently defined using Rodriguez's formula. So it's a high derivative of x squared minus 1 to the power L, and multiplied by these terms out front here. But you see, all that's involved is x and these various factors and coefficients in here that are all dependent only on L and M. Let's look at some of these associated Legendre functions. For example, for L equals 0, we have simply one function here. This is L equals 0 and M equals 0 in here. And that function is rather simple. It's just 1. For L equals 1, we can have this here. This is the 1 down here is the L. We've got M equals 0. And that function is just x. For L equals 1, M equals 1, this function is 1 minus x squared all to the half. And for L equals 0, M equals minus 1, this function actually is really the same as that function up there, but for formal reasons it happens to be defined with a minus a half in front of it. But in real terms, these two functions are actually the same function. For L equals 2, then for L equals 2, M equals 0, we have this simple 1/2 of 3x squared minus 1 function. For L equals 2, M equals 1, we have 3x into 1 minus x squared, all square rooted. And for the minus 1m version of that, we actually really have the same functions here and here, but for purely formal reasons, they're defined with different coefficients out front. So again, the minus m and m functions are really the same function. And for L equals 2, M equals plus 2, we have this fairly simple function here, 3 times y minus x squared. And similarly, for L equals 2, M equals minus 2, we have essentially the same functions here, with just for formal reasons, a different coefficient out the front. Now, we can see that these functions have the following properties. If you look at all of these that we've just written out, the highest power of the argument x in the function is always x to the power L. The functions for a given L, for plus m and minus m, are really identical functions, other than for formally numerical prefactors that are somewhat different. But that's of no physical significance. Less obviously, if you look at these functions between minus 1 and plus 1 of the argument, and not including the values at those endpoints, then these functions have L minus the modulus of m zeros in them. And that will turn out to have some physical meaning that we'll see later on. So the eigenfunctions of L squared then, putting all this together, our eigenequation was this equation then. And we figured out that the L here has to be this integer that goes from 0 on up for positive values. And these functions, y, l, m of theta and phi, are known as the spherical harmonics. And these are the eigenfunctions of this equation. And after normalization, these spherical harmonics can be written out as these associated Legendre polynomials here are e to the im phi from the phi part of the problem, and some prefactors out front to get the normalization right. So as I said, L has to be 0 or 1 or 2 or so on, any integer, and m has to be an integer that lies between and including minus L and plus L. And the eigenvalues of this equation, as you can see, are h bar squared times L into L plus 1. So we've solved this L squared equation here for its eigenfunctions. They are, within some constants, the associated Legendre functions of the cosine of theta times the exponential of im times phi. As is easily checked now, these spherical harmonics are also eigenfunctions of the LZ operator. Explicitly, if we take the LZ operator and operate on the spherical harmonics, then we're only really working with the phi part here, and as we figured out before, we've got an e to the im phi in this function, and that is indeed one of the eigenfunctions of the LZ operator with m as an integer. And the eigenvalues of LZ, as we found before, are just mh bar, so this works. It makes no difference, of course, to the LZ eigenfunctions if we multiply them by any function of theta, and of course inside the spherical harmonics, there is a function of theta that multiplies the function of phi, but it doesn't make any difference to these functions being eigenfunctions of this purely phi equation.